Hello guys, welcome back. We are beginning our Algebra 2 series now. This will be the first video in our full Algebra 2 course here at Forward Ed. You can visit us at forwardlearning.com, that's with the number 4, and enroll today. Now let's take a look at our scope and sequence. We're beginning, of course, in Chapter 1. The foundations for functions, and then we'll move on to linear functions in Chapter 2. We have quite a bit to cover here in Chapter 1. Our first lesson in foundations for functions will be sets of numbers. So essentially, real numbers can be classified into nested subsets, like natural, whole, integer, rational, real, irrational. And a single set of numbers can be described in multiple equivalent ways. We'll be exploring words, roster notation, interval notation, and set builder notation in this lesson. So you classify a number by identifying the most specific subset that it belongs to, and then you represent a set by choosing the most appropriate notation for the context. And that's essentially what our lesson is. All right, so, but before we begin, I want us to cover a few foundational skills. A bit of a warm-up here before we are jumping straight into Algebra 2. All right, let's take a look first here at our vocabulary. The big idea in our first unit is that we're wanting to apply properties and operations of numbers to solve problems. And we're wanting to develop symbolic and graphical representations of functions, as we're looking particularly at functions here in our first unit. All right, so order real numbers, simplify algebraic expressions with exponents, use functions and their graphs to represent situations, explore transformations, etc. Now, before we jump into all that, we really need to make sure our number sense and prerequisite skills are ready. That's what our section is here. Are you ready? The vocabulary match is our first section. So we have algebraic expression, opposites, origin line, variable. Let's go ahead and match our correct terms here. Algebraic expression is a mathematical phrase that contains one or more variables. Opposites are two numbers that are equal distances from 0 on a number line. Origin is the point in the coordinate plane where the x-axis and the y-axis intersect. And a variable is a symbol that represents a quantity that can change. All right, so opposites and origin occur when we're plotting points and finding absolute values. On the number line, for example, the opposite of 5 is -5 as we go from the other direction. The absolute value, though, is the distance from 0, which is 5. Now, in our next part, we're converting fractions to decimals. Excuse me. We're converting fractions to decimals. Let's practice on that. We want to make sure we can do that easily, seamlessly, accurately, because ordering real numbers requires us to compare decimal forms. So 3/10 as a decimal, we move that decimal place over. We're dividing by 10, so it's just over 1 to the left. For 0.3, or 3 divided by 10, in other words. So 3/10 here means that the digit 3 is in the 10th place. 3/5 as a decimal. Now 5 doesn't fit into 10 the same way, but it does divide into 10 evenly. So let's think of equivalent fractions. For example, which fraction would be equivalent, or which fraction would have a denominator of 10? Let's multiply both by 2. 3 times 2 is 6. 6/10. Now, how do we write that as a decimal? That's easier to write since we're dividing by 10. 0.6. Move that decimal place over once to the left. What about -4/3? This fraction will not terminate. So we can perform our long division and see which pattern emerges from the math. So let's divide 4 by 3. And see what happens to the remainder. 3 times 1 minus 3 is 1, so that 1 becomes our numerator, 3 becomes the denominator. 1 1/3, 1 remainder 1, and the 1 would keep dividing to give another 3, so it would repeat over and over and over again in our decimal form. For example, 3 into 10, and we'll have that 1 pattern over and over again. So we do see a repeating decimal there. With 1.3, let's put a repeating bar over our 3, over our 3 there to show that it's repeating. That's called an overline bar. All right, so overline bar written, it means 1.33333 on forever. So a repeating decimal has a block of digits that cycle on forever. That's our definition. And our bar over the repeating digit is our standard notation. And by the way, repeating decimals are rational numbers. They can be written as fractions. How about 5 3/4? 5 3/4. Oh, by the way, this was a negative. Let's not forget to attach our negative sign. And we can box in our answers so far. All right, number 8, 5 3/4. We are going to convert that fraction part separately. Then we can add the whole number. So what is 3 divided by 4? Think of quarters. 75 cents, right? 0.75. All right. So 5 3/4 now would be the whole part. To add that to that, let's replace the 0 with a 5. Now we're at 5.75. 5.75. All right, let's graph numbers on a number line. We have arrows that go in either direction infinitely when we're drawing our number line. There's a number line. All right, 3.5. Okay. That is exactly between 3 and 4. We know we go all the way to -3 or -4. That is our lowest value there. And then our highest value is 3.5. So 3.5 is between 3 and 4. So we should put it there between 3 and 4. So let's go ahead and start at 4 here, +4. And on the other side, we'll go all the way down to -4, or even -5. -5 all the way up to +4 here. -5, -4, -3, -2, -1, 0, 1, 2, 3. And of course, each of those are a tick. Here is our origin. All right, 3.5, that's between 3 and 4. Let's put a dot. And we can label that 3.5. -4 is way over here. Left side of 0. What about -12/4? We need to work that out, right? Don't forget our negative sign. And then 12 divided by 4 is 3. So we're looking at -3 to plot. And we have 3.3 with our repeating decimal on and on and on. So that means 3.333333333 is where we're looking at, which is close to between 3 and 4, but it would be before or after 3.5 is the question here. 3.3 over to 3.4 to 3.5. So we know it's going to be between 3.3 and 3.4. So 3.3. All right, let's go into number 13. 5/6 versus 2/3. All right, so to compare fractions and decimals, we convert the same form, usually decimals. For negatives, remember the higher the negative, the smaller the value. In the real world context, we can think of like debt would represent a negative value. The higher the debt, the more you owe, for example. Can you add debts together and they become more debts? Yes, that's what adding negatives is like in the real world. So when we're comparing our fractions here, we want to use a common denominator. In this case, it would be 6. We are looking at our multiples of 6 to see if 3 will go. Yeah, 3 will go into the first multiple of 6 there. So let's use our common denominator of 6. Now we're comparing 6 times 1 times 5 to 3 times 2 times 2. Now we're comparing 5/6 to 4/6. And 5 is greater than 4. We can just compare the numerators once we get those two equal denominators. All right, so we found our greatest common denominator. That's our skill. What about 3 and 7/9 versus 3 and 10/12? Now, both of these mixed numbers do have a whole part 3. So let's compare only the fractions. We see 9 and 12 for our denominators. So let's use our common denominator. If we go up by 12, 12, 24, 36 will be our first one, right? Between that is our common denominator. Nine times 4 is 36. 7 times 4 is 28. 12 times 3 is 36. 10 times 3 is 30. Now we're comparing the 28 over 36 to the 30 over 36. Easier to compare now. 28 over 36 will be, 28 over 36 will be less than 30 over 36.